Hello. Let's see if this works today. So for today, we will be solving a nuclear atom, which is structure 1.2. And I have decided that I will split my practice questions into SL and HL, so that one live stream we're solving only SL content, another live stream only HL content, so that it's easier for you to navigate. Yeah, so obviously if you're doing HL, you have to do both SL and HL. So today we'll be solving structure 1.2 nuclear atom, and I have compiled this worksheet from savemyexams.co.uk. You could check them out. Yeah, they have lots of practice questions. This is my second attempt to record this live stream. Yesterday something went wrong. I solved everything and then I noticed that half of my video was frozen. So today I'm checking it out. Hopefully everything will go fine. If not, I'm not recording it again. Okay, so let's just dive in. Yes, I have some multiple choice questions first and then some open response. Right, well, let's start. And the links to these worksheets that I've used would be linked at in the description of the video of this video. So first question, in which of the following species are the number of protons, neutrons, and electrons all different? Okay, and we need the periodic table, which I forgot to open. Okay, let's see. Periodic table there. Right, so what do we do? I'm still there, right? We need to find the species where number of protons, electrons, and neutrons are all different. So I will just write down the number of protons, neutrons, and electrons for all of the species. Okay, so let's start with sodium 23. So on the top you have the mass number, which is the number of protons and neutrons together, plus is the charge, and atomic number or the number of protons we can find from the periodic table. So we go to the periodic table, find sodium, there it is, and atomic number is the top number. Yeah, so it's top, yes, 11. And you write it at the bottom so that your life is not too easy, right? Okay, so number of protons is 11. Neutrons would be 23 minus 11. So it's 12. And electrons, okay, so about electrons. In a neutral atom, the number of electrons equals to the number of protons. Here it's, well, it would have been 11 if it was just sodium without the plus, if it was just sodium 0. But since it's plus, plus means that the atom has lost 1 electron, so minus 1. So 10 electrons. Why are you subtracting an electron? Well, because electrons are negative, yes? So if the atom, well, if the ion has a positive charge, it means that you've removed something negative, and that something is an electron, so 10. And this is actually the answer, right? Because we need species, which of the following species are the numbers of protons, neutrons, and electrons are all different. So that's A. Let's do the rest just for the sake of practice. Aluminium, but obviously in the exam you don't do that, right? you just choose A and move on. So aluminium 27, no charge, yeah, so it means it's 0. Finding aluminium, there it is, 13 protons, and I put it at the bottom, so protons is 13, neutrons is 27 minus 13. And electrons are 13 because there is no charge, which means that electrons equal to protons. Then fluorine minus 1, fluoride. 19. Yeah, and why is C not an option? Because protons and electrons are the same. Yes, and we need different. Okay, fluorine has atomic number of 9. So 9 protons. Neutrons would be 19 minus 9. And electrons would be, in a neutral atom it would have been 9, but it's 1 minus. You see the charge is 1 minus, so it's plus 1 electron. So 10 electrons. So you see it's not an option because it has equal number of neutrons and electrons. And finally sulfur 2 minus 32. Periodic table, sulfur is here, so 16 protons. Okay. 16 protons. Neutrons is 32 minus 16. 16, and electrons 16 plus 2, right? Because the charge is plus 2, so they've added 2 electrons, which is 18. 18 electrons, so equal number of protons and neutrons. That's why it's not an option in our question. Next, the atomic number of an element gives the number of protons in the nucleus, which is also equal to the number of electrons. Which statement explains why atoms are neutral? One actually important thing to know, yeah, when they say atom in the question, they mean neutral thing. They mean that it doesn't have any charge. Just like the word atom means that it's like by default it's neutral. Right. So the question, which statement explain why atoms are neutral? Let's look through the options. A, one proton has a mass 1,840 times greater than one electron. That's correct. That's a correct statement, but it doesn't explain why atoms are neutral, right? So when we talk about neutrality, we talk about charges. The charge on an electron is equal and opposite to the charge on the proton. That's correct. And that explains the neutrality, right? Because if we have equal number of protons, which are positively charged, to electrons, which are negatively charged, it would mean that protons sort of cancel out all electrons, and overall there is no charge. Let's look through other options. Again, in the exam, you don't have to look through other options unless you have time and you're confident you're on time. Yeah. C, the difference in charge between electrons and protons is balanced by the neutrons. That's completely wrong. Neutrons are neutral. Electrons are spread out in shells around the nucleus, while protons are concentrated inside the nucleus. That's true, but doesn't explain anything. So B. Next. Which statement correctly describe the distribution of mass and charge in the atom? The negative charge is concentrated in one area outside the nucleus. Is that right? My imaginary followers actually still made it private. Okay, yeah, so I hope my imaginary followers, they said that, no, that's wrong, right? It's not concentrated in one area, it's spread out like in the shells, right? So it's not in one area, so not one. And here, if it's not 1, it must be 2 and 3, so C. But let's check. The mass is concentrated inside the nucleus. Yes, protons and neutrons, it's like well, it's the most of the mass of the atom, yes, and that's all in the nucleus. The negative and 3 negative charges spread around outside the nucleus. Yes, that's true. So actually 1 and 3 cannot be correct at the same time because they're contradicting, right? This is concentrated in one area and this is spread around. Everything else is the same. So 2 and 3, C. Next. The isotope of cobalt is used in treatment of cancer cells in the body. Which statements about this isotope are correct? They even told us the number, atomic number, which is from the periodic table, by the way. Yeah, so cobalt 27. All good, all correct. So which statements are correct? Also check whether they ask about correct or incorrect statements. So the charge on the nucleus is 27, correct. Yeah, atomic number 27, charge is 27. There are 33 neutrons. 66 minus 27, that's the neutrons. So that is what? That is no, not 66, 60. 60 minus 27, yeah, that looks like 33. So this is correct. Yeah, top number minus bottom number. And it has the same number of neutrons as other isotopes of cobalt. Well, that's wrong, because by definition, isotopes are atoms of the same element that have same number of protons but different number of neutrons, so they cannot have the same number of neutrons, so not 3. It means that it's 1 and 2 only. Next question. Which row correctly describes subatomic particles found in magnesium 26 2+? Okay, let's see. So magnesium 26 2+, from the periodic table, magnesium's atomic number is 12, so 12 protons. Protons are 12, neutrons, let's do neutrons. Neutrons would be 26 minus 12. 14, and electrons would be the same as protons, so 12 minus 2 because it's plus 2, so 10. It's then 12 protons, 14 neutrons, 10 electrons, so B. Okay, fine, B. Next is paper 2 questions. Paper 2, open response. Right, first question. Use your knowledge of subatomic structure to complete the table below for the particles found in an atom. Protons, relative charge is +1. Relative charge, guys, right? So it's not the absolute charge. It's relative to just, well, if you just take a proton, it has a positive charge. Let's set it as 1. Neutrons are not charged. Electrons have exact same charge, but opposite to the proton, so -1. Then relative mass. For proton, it's 1. Again, it's not grams, it's not any real units. It's just if you take a proton, whatever mass it has, we'll set it as 1. If you set it as 1, then neutron would also have a charge of 1, and electron would be 1 over 1840. Yeah, so 1840 times less than proton or neutron. Approximately 1 to 2000, yeah. Right, next. The actual mass of protons, neutrons, and electrons is given. Yeah, so this is the real mass. Yeah, this is what it is in kilograms. Calculate the mass in grams of a nitrogen molecule. 1 mark. Well, to be honest, I think it's not 1 mark, because that's quite many calculations. I would say just ignore the 1 mark thing. Yeah, but it should be more, I think. Right, the actual masses are given. Calculate the mass of 1 gram of nitrogen molecules. Okay, what's a nitrogen molecule? That's a pre-IB knowledge. That's like GCSE or MYP knowledge. You need to know that nitrogen molecule is N2. Yeah, so some molecules are diatomic. N2, H2, O2, Cl2, Br2, I2, F2, maybe something else, which I forgot to mention, but nitrogen is N2. Okay, so let's look at, yes, and also when I was solving this yesterday, hope I am still there. Yes, am I still there? So when I was solving it yesterday, I paid attention to the fact that they forgot to say which atoms we have. Yeah, so I decided yesterday that I would take atom of nitrogen 14,7, but in the exam they would tell you which atom it is. Yeah, so let's say it's nitrogen 14,7, the most common isotope. And so this is 1 nitrogen, right? And if it's 1 nitrogen atom, then it would have 7 protons, 14 minus 7, 7 neutrons, and 7 electrons, right? That's for 1 nitrogen atom. Now, if you have a nitrogen molecule, there are 2 atoms of nitrogen, which means that it has 14 protons, 14 neutrons, and 14 electrons. Yeah, so everything is doubled. Okay, checking if I'm still, yes, I think I'm there. I hope I'm there. Right, so a nitrogen molecule has 14 protons, 14 neutrons, and 14 electrons. And we know the mass of every single subatomic particle, right? And I just find the mass of 14 protons plus the mass of 14 neutrons plus the mass of 14 electrons. And that would be the mass of the molecule. Of course, we will find it in kg first, and then they ask to convert it to grams. Well, let's do it. So mass of nitrogen molecule would equal to, so 14 protons, 14 times mass of 1 proton, 672,622 times 10 to the minus 27 plus 14 neutrons times almost the same. Yeah, slightly different, but almost the same. 1674927 times 10 to the minus 27 and plus 14 electrons. 14 times mass of an electron. 14 times 9109383 times 10 to the minus 31. I'm not calculating this, okay? You can do it. I trust you can press the correct buttons on your calculator, so you just calculate that. But what's important? It's important that the mass that you get, it would be in kilograms, right? Because we have kilograms here. So this is the mass in kg, and they ask for the mass in grams. So how do we convert kilograms to grams? 1 kilogram is 1,000 grams. 1 kilogram equals to 1,000 grams, which means that to convert kilograms to grams, we multiply it by 1,000, and you'd get this mass in grams. Okay? I hope that's fine. I'm not calculating. You can do it. I believe in you. Okay, next. Next question. Oxygen consists of three stable isotopes, oxygen 16, 17, 18. When they write it like this, they show the mass numbers, obviously, right? So oxygen with the mass number of 16, 17, and 18 are different isotopes. State the particles present in each isotope and outline what differences would be expected in the chemical reactivity of three isotopes. Not reactivity, but properties, okay? Chemical properties, they meant. I'm not going into details what's the difference now, but when we study trends in reactivity, maybe there we would discuss this, but for isotopes you need to know the properties, not reactivity differences. Okay, so first, what do we need? We need, it's 2 marks, yeah, state the particles present in each isotope. Let's do that, that's the easiest. So oxygen 16, remember mass number is written at the top, 17, 18. And then we write protons, neutrons, electrons in each. So oxygen is in the periodic table, its atomic number is 8, which means that all of them have 8 protons. So 8, 8, 8. And neutrons, for the first one, it would be 16 minus 8 is 8. For the second, 17 minus 8 is 9. For the last one, 16, not 16, 18. 18 minus 8 is 10. Yeah, that's the number of neutrons, and electrons equal to protons, so 8 for all of them. Because they're not charged, right? So no charge. If there's no charge, then protons equal to electrons. Then, okay, that we said. What else? Outline what differences would be expected in chemical properties of these three isotopes. This is a very common question, and it might sound intimidating, but you just need to know that chemical properties are defined by the number of electrons in the outer shell, okay? So all of these guys have 8 electrons, which means that they have the same number of electrons in the outer shell, which is actually 6. But even if you don't know that, you see same number of electrons, which means that same number of valence electrons or electrons in the outer shell, which means that we would expect them to have similar properties. It's the same as, you know how, for example, group 1 metal, they would react with like water, acid, or whatever in approximately the same way. Yeah? So they would have similar chemical properties, not reactivity though, but chemical properties. Okay, so the answer to this would be that there would be no difference, or like no difference in chemical properties, and in chemical properties and I think we have to explain. I would explain it in any case, even if they didn't ask explicitly. Yes, let's explain. Because all of these isotopes have the same number of electrons in the outer shell. All three isotopes have equal number of electrons in the outer shell. 2 marks. Next question. Suggest why some elements have several isotopes and others, like fluorine, have only one known isotope, known as monoisotopic elements. I'm not sure how you're supposed to know it, but it's like 1 mark common sense question. Yeah, so we can assume that isotopes of fluorine are not stable. Yeah, so you know there is atoms can decay and turn into other elements. Yes, so fluorine can turn into something else if its nucleus would decay and disintegrate. So I would say that just 1 mark. Yeah, so fluorine's isotopes are not stable. Other isotopes of fluorine are not stable. Okay. Next question. Nitrous oxide is used as a sedative in dentistry and has the formula N2O. Different sources of N2O contain different ratios of N14 and N15. State the name of the instrument used to distinguish between N14 and N15 and outline two characteristic differences seen in the analysis of N14 and N15. You don't need to know how mass spectrometer works in details, right? But you do need to know, well, why we're using it. Yeah, so, well, obviously the instrument name would be mass spectrometer. Mass spectrometer, okay. And then what does this device do? Well, this device, it would measure isotopes and their abundance. Yeah, so what it does, it measures a mass to charge ratio of the isotopes of the ions, yeah, that we're making. But again, they removed the entire like description of of how mass spectrometer work. That's why I don't want to give you any like information that you don't need anymore, but maybe it's worth knowing that in the mass spectrometer you need to form ions first. Yeah, so all those nitrogen atoms would be turned into ions and it would register mass to charge ratio. Essentially, we assume that okay, all ions have a 1 plus charge, which means that the mass to charge ratio would just equal to the mass of the particles that we are like detecting. Yeah. But still, I would use the word mass to charge ratio. That's what this mass spectrometer detects. So it detects mass to charge ratio and hence the number of isotopes present and the abundance of each isotope. Okay, that's what it does. For HL, you actually need to know, I'll just quickly sketch a graph. Yeah, so for example, if you do a mass spec, if you like plug those nitrogens into the mass spectrometer, you would see something like this as an outcome. So you'd have M2Z ratio, and here you would have relative abundance or percentage abundance, like some abundance. Yes, so it's like how much of those isotopes you have. And because there are only two isotopes, you would have two lines. So one line would have higher abundance, which would be nitrogen 14. Another line would be smaller abundance, which is nitrogen 15. Yeah, because you just have less of the nitrogen 15. So for example, this graph shows that there are two isotopes, 14 and 15 mass number, and that the abundance of 14th isotope is larger than 15th, and it would tell you like how much exactly it is. I think it's in the next question coming. But for SL, you don't need to interpret the graphs, okay? Just know what it does. So mass spectrometer finds a mass to charge ratio of isotopes. And their relative or percentage abundance. And outline two characteristics. Yeah, well, outline two characteristic differences. So mass and charge ratio would be different. Yes, so we just have to say what would be different. So mass to charge ratio of isotopes would be different because those are different isotopes, and percentage abundance would be different between the two. Would be different. Okay. Next. A sample of nitrous oxide, it was the same N2O as before, was enriched so that it contained 4% by mass of N15. Calculate the relative molecular mass of the resulting nitrous oxide. Right. In this question, they just ask for molar mass of N2O. Normally, if it was any other question, you just go to the periodic table, find nitrogen's relative atomic mass, times it by 2, and add oxygen. Here you cannot do it like this, yeah, because this is not a regular nitrogen sample. You see they've went into all this trouble to enrich it with N15, right? So it must be heavier probably than the normal one. So the first thing that you have to do, and also you see 2 marks. If it was just finding molar mass of N2O, very suspicious for 2 marks, so no. Doesn't work like that. Okay, so here first we need to find the relative atomic mass of that particular sample of nitrogen, right? How do we do it? Well, let's see. They told us previously that this sample had only two isotopes, N14 and N15. So if for N15 abundance is 4%, then what would be the abundance for N14? Well, 100 minus 4, right? 96%. So everything else is obviously N14 because there are only two isotopes. They told it here. Contain two different ratios of, yeah, so these two isotopes. Nothing else. And then we find relative atomic mass for nitrogen in this sample. So it would be mass number times abundance. So 15 times 4 plus this mass number plus this abundance. 14 times 96 and divide by the sum of the abundances, 4 plus 96. Be very, very careful. It's not always 100, okay? If it's percentage abundance, it is 100 most of the time, but then they can set the most abundant isotope as 1 or as 100%, and then it would be something else. And these questions are very, very common, especially in the recent years, when this number at the bottom is not 100, okay? So just add all the abundances and divide by that number, whatever it is. Well, here it's 100. All right, well, I will calculate it. Yes, my calculator is here, so I will calculate. 15 times 4 plus 14 times 96 over 100. So it's 14.04 for nitrogen, right? And in the periodic table, it would have been 14.01. So that would have been a mistake because they have enriched it with a heavier isotope. That's why it's heavier than normal. Well, yeah, and then you just find molar mass of N2O using this 14.04. So 14.04 times 2 plus oxygen is 16. 0, 0. Remember all molar masses to 2 decimal places in IB. 04 times 2 plus 16, 44.08. 44.08, so 2 nitrogens and 1 oxygen in that molecule. Next. Yes, this one I think I decided to skip because it's first ionization energy. I have a feeling it's HL. I might be wrong because I haven't memorized all the differences now because it's the new syllabus, right? So I'm not sure. Yet I think it's HL. I'll skip it. And then next, an atom has twice as many protons and twice as many neutrons as an atom of N15. Determine the chemical symbol for this atom, including the mass number, and deduce the number of electrons. That is a good question. So nitrogen 15. So we have to, let's just find protons, neutrons, and electrons for this guy. And then we just double it and see what element that would be. So nitrogen is 7 protons. Neutrons would be 15 minus 7, which is 8 according to my mental math. And actually they don't care about electrons. No, deduce the number of electrons. They do care. Okay, so electrons here, it's 7. But for this one, we don't need it. But okay, never mind. So, and then for the element they're asking about, so let's say it's element X. So the protons would be twice. Yes, so an atom has twice as many protons, so 14. Twice as many neutrons, so 16. And well, electrons must also be 14 like protons. And let's see what atom it is. So an atom with 14 protons is silicon. This guy. So the answer is silicon. And 14. And then, okay, and then what's the mass number? Mass number would be 14 plus 16, so 30. And electrons is 14. Okay, silicon 30, 14 with 14 electrons. Next question. A and B are different chemical elements from different groups in the periodic table. State why AM and AN have identical chemical properties, but AM and BP have different chemical properties. 3-mark question. Okay, for 3-mark question, we have to write like at least 3 statements explaining whatever they're asking, yeah? So what do we need to explain? State why AM and AN have identical chemical properties, but A and B have different chemical properties. Remember, we said that chemical properties are defined by the number of electrons in the outer shell. Well, AM and AN, since they have the same chemical symbol, which is A, it's like a fake one, but still it's the same. It means that it's the same element. So AM and AN are isotopes of the same element. Let's write it down and hope that it's the first mark. So AM and AN are isotopes, which means that they have they have the same number of valence electrons. I would say that's the second mark. Okay, I will not write it as mark divided by mark. So I think isotopes is 1 mark, so they have the same number of valence electrons. It's the second mark. Or electrons in the outer shell. And that explains the identical chemical properties. Yeah, so that's why they have identical chemical properties. I guess we've done 2 marks, right? So isotopes, and we explained why they have identical chemical properties, and then why do A and B have different chemical properties? Well, obviously A and B are different elements, and you see what they say? They are in different groups. What does that mean? Well, that means that they have a different number of valence electrons. A different number of valence electrons means that they would react in a different way. Mhm. Okay, that's the third mark. So AM and BP are elements in different groups. So they have different number of valence electrons. Or outer shell electrons. Electrons, which means they have different chemical properties. Okay, I'll just tell you one more thing. Different chemical properties. So this you don't really have to write, yeah? So like identical chemical properties, different chemical properties, because it's already in the question. So they are not the examiners are fine. They are quite intelligent. They would understand what you mean, right? But it's just like for the sake of explanation, I write it a little bit more in a little bit more detail so that you understand better. But in the exam, I would maybe don't write that and just stop like this. Yeah, okay. Next question. This is a similar question. Atoms made up of 3 something something. Calculate the mass of an atom of carbon in kg. You see, this is 2 marks, and this doesn't even have conversion unit. So I think that one with nitrogen was even, and the molecule of nitrogen should have been 3 marks at least. I skipped this one, so you just calculate the total number of protons, neutrons, and electrons in the carbon atom, multiply those by masses, and add, similar to what we've solved for nitrogen. Not solving this one. State the difference between these 3 isotopes in terms of subatomic particles. I don't know. I think it's fine, right? So you just find the atomic number in the periodic table. So okay, let's do it quickly. So for carbon, atomic number is 6. Yeah, let's just do it because it's like the most common question that you'll get. Let's do it one more time. And 14, and state the difference between these 3 isotopes in terms of subatomic particles. The difference between, so the difference is in the number of neutrons, right? So we just calculate the neutrons. So protons is 6 for everything. In neutrons, it's 12 minus 6 is 6, 13 minus 6 is 7, 14 minus 6 is 8. So the difference is in the number of protons. So the answer would be they have a different number of protons, not protons, neutrons. A different number of neutrons. The difference is in the number of neutrons. I'm not sure what I said before. Number of neutrons, and we say how much? Yes, so 6 for carbon 12, 7 for carbon 13, 8 for carbon 14. Next question. And I think that's the last one. Yes. A sample of cerium was analyzed in a mass spectrometer. The relative abundances of the three of the four main isotopes that were identified are shown in the table below. A sample of cerium has four isotopes that have a known relative abundance. This sample has an AR, relative atomic mass, of 140.12. Use the data from the table to calculate the mass number and the percentage abundance of the cerium isotope, MCE. Okay, that's 4 marks. Well, let's see what we do. So this is like a question that is opposite to the one that asks to find relative atomic mass. Yeah, so here we need to calculate, we have the relative atomic mass, we need to calculate abundance and the mass number. Right, okay, well, let's do it. So this is percentage abundance, which means that the sum should be 100, right? So percentage abundance of cerium M, it's 100 minus all other isotopes. Yeah, so 100 minus 0.19 plus 0.25 plus 88.45. Right, let's see what that is. So 100 minus 0.19 minus 0.25 minus 88.45. That's 11.11%. It's here, 11.11%. And then normally, how do we calculate the relative atomic mass? So we multiply abundance by the mass number, right? So it's this number times this number plus this number times this number, and you add it up throughout all the isotopes. And we know so we know the relative atomic mass. So that's what I will do. I will just say that 140.12 equals to 136 times 0.19. Yeah, so this times this plus 138 times 0.25 plus 140 times 88.45 and plus what? Plus m times 11.1. I mean 11.11. And divided by the sum of abundances. Here we don't have to check because, well, obviously here it's 100. We set it as 100. Yes, and then we just find m. I know you can find it using like some calculator thing, so you just plug it in. You just plug it in and calculate. I don't know if I should do it. I think I will do it, maybe. Yeah, I'll do it and then you can check. But I'll do it quickly so I might make a mistake. I will do it old-fashioned way how I would do it in math if I didn't have any fancy, I actually don't have any fancy calculator, so that's why I just do it old-fashioned way. So what I'll do is I will multiply both sides by 100 and calculate these things. So 136 times 0.19 is 25.84. 138 times 0.25 plus 140 times 88.45. And then this, I obviously cannot add it, just 11.11 m, right? It would be my unknown. And then I calculate, so I say 11.11 m equals 2. And then I, like everything that was on this side, like I would put it to that side with the minus. Or I'm not sure if I should be explaining this. You can figure it out, right? It's just, I don't know which grade math, maybe year 6, maybe even less. But I might get it wrong still because, you know, so many numbers. 6, and so m would equal to 1568.66 over 11.11. Which is 141.2, but we will round it to a whole number, so 141. 141, that's m, yeah, so that's good enough, yeah, because we had isotope 136, 138, 140, so 141, it fits nicely here. All right, that's the last question. I let everyone go as if I was holding you here. And next time, we would probably do, for IB, we would do HL part of the same topic. There are not many questions because there are not many things on HL for this nuclear atom. It's, oh, actually, hydrogen emission spectrum was at 1.3. Yeah, I think there are just calculations with all the like energies and stuff. Yes, so next time we do HL for 1.2, and then also I planned a few streams on A level because those students say that they are left out a bit, but more difficult A level stuff we would also solve. Right, I let you go. I might abruptly cut myself off because I'm not sure how YouTube works. I think it cuts me off earlier than I assume it would cut me off. So take care and see you next time. And I'll wait a bit if I'm just sit here.